today we've got two experts actually. We've got Julian Brown and Matt Meckes. And Julian today is going to something quite exciting actually. But before I go into that, Julian, he's a technical architect. Before I carry on, he's a technical architect. He's one of our board members at Cohesis and a founding member of Hive. I found that through stalking his LinkedIn. Julian's going to do something very exciting. He's going to actually demonstrate how to build a blockchain. And from what he explained earlier, his kids got it. So there's hope for us. For those of you that don't get blockchain yet, there is hope for us. Julian? Yes.
Right. Hello. Yeah, so this is a slightly ambitious presentation. Actually, let me start by describing my relationship with blockchain. So about a year ago, I went to work for a venture capital company who had this idea to revolutionize the agricultural industry by collecting data on farms, so animals that get born, things that animals get fed, medicines that are given to animals, plants that get sown and harvested, into a database of some description so that supermarkets and the end consumer would be able to access that data, so you would know if you bought a steak in a supermarket that was genuinely from an organic, free-range, non-antibiotic animal, which is impossible to do today. And blockchain just seemed to be like one of those technologies that would fit the problem space very well. So as part of that project, we built a blockchain from scratch. We took the original spec and we actually built a blockchain. And during the process of building the blockchain, I came to understand this gap between the hype and the reality. And in the back of my head, I kept thinking, but for all of the words that get used when people talk about blockchain and cryptocurrencies and so on, the concepts are actually quite simple. And so, like I say, in the back of my head, I sort of set myself this challenge, which is about to be proven one way or another tonight, as to whether it would be possible to explain everything about blockchain from first principles without necessarily getting involved in a lot of the technical hoo-ha. So, all you need to know before you watch this presentation is, all I'm expecting rather, is that you've seen articles like this one. Blockchain's going to change the world. One of my favorites. Blockchain's going to solve the crisis in the NHS. There's a new technology of trust. Anyway, these are from all major publications, the kind of publications that investors read, CEOs read, and obviously there's a lot of hype. So all I'm expecting is that you've seen something like that. I'm not expecting any more knowledge than that. And there's no code in this presentation. I mean, there is code in the presentation, but you don't actually see any of the code. So let's go right back to the beginning of blockchain. When I decided that we would implement a blockchain, I always do this with any technology. I try and go right back to the kind of its inception, because I always find that by understanding how things came to be, you can understand much more about how they actually operate. So roughly 10 years ago, about this time, a person called Satoshi Nakamoto wrote a famous paper. The paper is not actually about blockchain, it's about Bitcoin, and this presentation is not specifically about Bitcoin, although I can't help but mention it. So the paper was written at the end of 2008. In early 2009, the first code was written according to the specification in that paper. And the two mysteries of, or rather the main mystery around blockchain is who Satoshi Nakamoto was, because he doesn't actually exist, or her, or it could have been a group of people. The email that the paper was published with, I checked this out the other day, is actually, it's just a hosted email service. So he wasn't part of any particular organization. And the only thing that we have really to date the work that happened in the early days of Bitcoin, so there's some code and there's some emails floating around, is the fact that this newspaper from January 2009, that headline is embedded in the blockchain, so we know for sure a blockchain couldn't have existed before that date. Everything else is kind of up for speculation as to who he was and exactly what happened to him after 2 years of engaging in the blockchain community. So this is what's so strange about this, how significant blockchain is, and it underpins, depending on your view about Bitcoin, an extremely important currency, potentially, and yet the guy or individuals responsible created a fake name, published some stuff, wrote some software, and then 2 years later just said, we've moved on to other things. And the reason that it's created so much excitement is because we don't have teleportation. This is all going to make sense in a second. We don't have teleportation because in the world of money, so before any digital concept of money, this is not a picture of a pound note. This is a picture of a piece of paper given to servicemen roughly 100 years ago to use inside canteens on army bases, and it represents the value of a pound. And the reason it works really well as a value exchange is because I can have some of these pieces of paper in my pocket, and when I go and buy a pint of milk, which is roughly £1 these days, I take the piece of paper out of my pocket and I hand it to the person with the milk, and they hand me the milk, and the value is exchanged at that moment. And the fact that it's physical means that I can't spend what I don't have, because as soon as I've handed that pound over, I don't have it anymore. And if there is no milk in the store, I put the pound back in my pocket, and there's no concept of me accidentally spending money on goods that don't currently exist. And what we do in the digital world is we typically use a database for this. So a database is really good at making sure you can't spend what you don't have, and you can't buy something that doesn't exist in stock. But we have a problem when you scale up to sites like Amazon, is that one database is not performant enough. Amazon famously 18 months or so ago passed 600, not transactions a second, but 600 sales a second. So each sale is made up of many transactions, so thousands of transactions. You can't do that on a single database. So our problem is when we distribute databases around the world in order to support our high-scale systems, the database on the left could be in New York, and when I take my money out of my account in order to give it to somebody else, for a few milliseconds, the database in Germany, for example, still thinks I've got my money. So my money is gone in one database and not in the other. So it becomes a technical problem of making sure the databases are synchronized, which, when you just have one, is relatively easy to do. When you have many, it's difficult. And if you imagine that you could snapshot databases at an instant in time, the database in Germany would still say, I've got my pound, and the database in New York would say that my pound is gone. So there is no concept of what the truth is. What's called in the technical papers concurrent common knowledge is a nigh on impossible thing to define. In fact, you get into the realms of physics where everything becomes relative. So we don't know what the truth is about the truth. And Satoshi Nakamoto's paper proposed a mechanism to fix that. And if it was true, then the entire world is revolutionized. I was a bit skeptical before I read the paper, because there are many mathematical theorems that prove that you can't have a database in New York and a database in Germany that will ever know exactly what the truth is at any moment in time. So in order to start understanding how a blockchain works, you need to understand this, which is a corned beef hash. Now, it's called a corned beef hash because you take corned beef and you hash it. Hash is from the original French word hacher, which means to take a hatchet to something. And you chop it up, and it becomes, it's still what it was. It's still corned beef in the sense that corned beef is still present, but you can't go back to the original corned beef, and in no way can you kind of reassemble what you originally had. So Alice and Bob are typically used in cryptographic stories. So Alice and Bob decide that they're not very happy about Brexit, and they would like to subvert it. You see a lot of people on Twitter talking about the Remainers trying to subvert Brexit. So how do Alice and Bob communicate with each other in such a way that they can successfully subvert Brexit without anybody else being able to interfere with their plans? Now, one thing they would need to do is they need to encrypt their messages. So when Alice sends a message to Bob, Boris Johnson can't get hold of that message and be able to decrypt it and then interfere with their plans. But Bob also needs to know when he gets the message and decrypts it that it definitely came from Alice and not Nigel Farage. So there needs to be some way that she can sign the message so that when Bob gets it, he knows, because Nigel Farage could have actually worked out what the encryption mechanism is, because encryption means I turn it into some kind of code and then I turn it back into readable English. And so Bob needs some way to make sure that what is in the message is definitely Alice's. So this is what the thought that passed through my head when I was first reading the blockchain spec a year or so ago. So imagine you didn't know anything about, imagine computers didn't even exist. How might you go and solve it? And I completely made this up, but it's just a sort of working example. So typically what you see when somebody sends a message to somebody else is they just use their initial. So if Bob gets a letter from Alice and she just signs it A, it's probably from Alice. If Alice gets a message signed B, it's probably from Bob. But if Boris Johnson had signed it, he'd signed his messages B as well. So Alice wouldn't know whether it was Bob or Boris Johnson. So you might do something like this. You might say, well, let's make it a bit more sophisticated. Let's include the number of letters in our name. So now Alice becomes A5 and Bob becomes B3. Maybe we could stick some vowels in. Count the number of Bs. So Bob's got 2 Bs, Alice has got 0 Bs. Change the letters to numbers, so A becomes 1 and B becomes 2. And then, just to make it a bit more fancy, we could just send it backwards. So you can see what's happening is I'm taking my hatchet, I'm hashing Alice and Bob, and at each step, it's getting harder and harder to go from what I've come up with back to Alice and Bob. In fact, by the time you get to the bottom, it's nigh on impossible to go back to Alice and Bob unless you understood the mechanism. And so all a hash is, and like I say, this is not a hash per se, this is just a way to think about it that doesn't involve reading the code of a hash algorithm. But computers don't need to do all of that kind of stuff, so they don't need to count A's and reverse stuff, because they store things in binary. So if Bob started to sign his name, so let's stick a B in there, B internally in the computer is a 0110010, and if he wrote his second initial, it would be 011011111. And what the computer can do is work out if the one at the top, if the row at the top contains a 0 and the row underneath it contains the opposite, so not the same, it always has to be different, so 0 and 1 or 1 and 0, then convert that to a 0 or 1. If it's 1 and 1, it's always 0. If it's 0 and 0, it's always 0. If it's 0 and 1 or 1 and 0, it's always 1. What's actually happened is, again, it's just chopping it up and it's converted B and O to the number 26. And then similarly, you could do that with any other combination of letters. Details aren't important, just that a computer can do more clever stuff than we can do. And if that was too complicated, just think corned beef, because it really doesn't need to be more complicated than that. So if you were going to, so that's how a hash works. If you were going to write a hash function, you obviously need to comply with some kind of specification. So a hash needs to be deterministic. That means if I put Bob in, I always get the same letters and numbers out. It needs to be fast, because I can't wait 24 hours to hash my input text. It needs to be irreversible, so if I put Alice in, I can't get back to Alice, not without guessing every single combination of letters in the universe. Uncorrelated kind of implies the same thing, so if I hash the letter A and then hash the letter B, I shouldn't be able to see a kind of pattern emerging, because that would be the beginning of a way to make it reversible. It would stop me having to guess and make me try and work out an algorithm to decode it. Collision free. So if I put Alice in, and I put something else in, I never get the same output, because then potentially somebody else could put in something different and end up with the same hashed output. And the fixed size bit, I'll come on to that in a sec. And then just to make the final point that this is not the same as encrypting. We're not trying to be able to get back. We're not trying to go back to whatever got put in. We're just trying to create a signature of what the input was. And it becomes much more simpler when you actually see a hash in action. So what you've got there is a box of data with nothing in it right now, and a hash. So that's the letters and numbers that get produced by the hash algorithm. And that, E3B0C44 blah, 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 is the hash of no letters and numbers at all. As soon as I put something in, A, that's the hash of A, B. So you can see it's now following all of the rules of the hash on the previous page. So that's the hash of hello. And if that little disk thing just memorizes what was in so it just gets saved in the bottom. So as I type hello you can see the difference between the two. And in fact, if I go back to what I said before about, just delete that. So that's the hash of A. If I save that, that's the hash of B. You can see that they're completely different. There's no way to kind of guess that one is one different in the alphabet than the other. Other important factor, if I insert Hamlet's soliloquy from the end of the play, a very huge piece of text, it's the same length as the hash for the letter A. So the algorithm is effectively losing information, because what we end up with is always something of the same size. And when Bob gets a letter signed with 2BD806C, there is no logical way to work out who that's from, because I can keep typing in things and hoping that it matches, and of course it's not going to. But if I type in Alice, you can see that the hashes match. So as long as Bob knows what to type in, he can then compare the two hashes, and he knows that that must be from Alice, or at least the letters that were put in are definitely Alice's. So that's all a hash function is. It's putting in some letters, getting some random numbers and letters back out. But they end up having some really interesting and useful properties. So let's say I start with my A. So there you go, that's the hash of the letter A. And if I stick another row in there, I can actually start to connect my text and my hashes, like I say, to create some interesting properties. So if I put a B into the second set of data and go back and change that A to ABC, you'll see that both hashes are changing, because that is a hash of ABC, that is a hash of B, and that hash, because a hash is just more text, letters and numbers. So I can hash a hash as easily as I can hash anything else. And why is that useful? Well, if I clean all those out, Alice and Bob might decide that their secret plan to subvert Brexit is to form the Follow Back Pro Europe group on Twitter, the hashtag. Then Alice breaks into the government building and steals the impact assessment documents and publishes them, which forces a general election. Bob stands for Prime Minister, and that's how they subvert Brexit. Now, these little locks allow me to make the screen remember what those hashes are, because, as is obvious, if I change Bob for Secretary of State, the hash is different. So I now know that that's been tampered with. But because the hash of each subsequent one after the first one is a hash of the previous hash and the previous data, if I change form FP group on Facebook, they all break, because the hash at the end is the hash of everything that came before it. But actually, I don't need to remember either of these two, because if I change anything, oh, hold on, let me unlock, clean out, save stuff. If I remember just the end bit, if I change anything anywhere, let's put that back, the last one always alerts me to the fact that that's changed. Clearly my Brexit joke is landing a bit flat, so I'm going to leave my Brexit analogy and move on to some more useful stuff, which would be something like a will. So as people get older and they create a will on a piece of paper, they would typically go and register it with a solicitor, and the solicitor would stick it in the safe and get them to pay some money and have it and notarize the will. And then a few years would go by and they might write another will, and they might use a different solicitor. When it comes time to actually trying to find the actual will that is currently relevant and legal, it turns out it's a really difficult thing to do. So if Bob decides to leave all his money to Alice, he creates a will, and in this case I've just created a hash of I leave all my money to Alice, but then maybe over time he gets really into cats and he decides to leave some of his money to Alice and some of his money to the cat's home. And then he falls out with Alice and he decides to leave all his money to the cat's home. By connecting the data and the hashes in the same way that I just showed, not only can nobody tamper with the will, because the hashes are a hash of the data and the previous hashes, they must have been created in that order. So in Bob and Alice's secret plan to subvert Brexit, the logical plan is to do it in that order. If you did it in another order, you wouldn't be able to subvert Brexit. But actually, in legal terms, this turns out to be massively valuable because now I can prove for sure that these things definitely occurred in that order and nobody's tampered with them. Two hugely important properties. Now, that's like a link of data, but actually if you wanted to do it really quickly, you can do it in a kind of tree structure. So imagine that down here was my different wills and different versions of wills, and then maybe over here there's documents about housing sales and whatever. This could be running on one machine, and I eventually end up with the hash of all of those documents, and then this is another hash of all of those documents. And because you can just hash a hash, I can then hash all the property stuff and all the wills, and then I can hash all the, I don't know, divorce papers, and I can hash all of the employment contracts, and I end up with one hash to rule them all, which it has exactly the same property. So if I change anything below, the top hash will tell me. If I fiddle with anything and change the order, then the top hash will also obviously be different. And this, in blockchain terminology, is a block. So in Satoshi Nakamoto's paper, interestingly, he never actually mentions the word blockchain. That was something that came along later. I think he refers to a hash of blocks, something like that. So we've got our block, and it ends in a hash, the top hash, but we can take that hash and then hash that hash with all the data in the next block, and in the next block, and in the next block. And the great news is if you're ever creating a data structure like this, it's extraordinarily fast. So a computer can do hundreds of thousands of these in a second without even pausing for breath, which is good, except if I was Bob and I wanted to go and fiddle with some legal document, if I've got a very fast computer, I could go right back to the beginning, change that data, then really, really quickly rehash everything all the way up to the end before anybody's noticed. And as long as nobody's put a copy of that hash in a safe, I can actually break the system. So it turns out that fast, if you're dealing with anything sensitive, it's not quite as good as it sounds, because fast means easy to fake. And so for that, what Satoshi Nakamoto suggested is the concept of mining, which really baked my noodle until I actually started to see the implementation. So we're back to similar structure as before, except now this is getting a little bit closer to what blockchain in Bitcoin actually does. So Alice gives Bob £10, Charles gives Bob £10, so Bob's now got 20 quid, and he owes Alice 10 and Charles 10, and then Bob pays Alice back £5, so he owes Alice 5 and Bob and Charles 10. Hashes, exactly the same. This is all real, not fake stuff, so if I change the first bit, everything else changes. So it's exactly as before. But now, instead of, we now want something to kind of slow everything down, because we want to put some kind of barrier with at the end of this chain of transactions to stop somebody else coming in and really quickly fiddling it, because Bob might want to go back and change that first transaction to say Alice only gave me 5, in which case I now don't owe her any money. And so that's where the concept of mining comes in. So if you get the data turning into a hash bit, and I think this was sometimes I think this is the stroke of genius, and sometimes I think this is where all the hype comes from and it gets completely misunderstood. But if you can take a piece of data and it has this deterministic hash output, what Satoshi Nakamoto said is, well, what if you kind of thought about that in reverse? What if you created some data that we don't know about yet and stipulated what the hash should actually look like? So let's just make it really simple. Let's say we're going to add some data to this chain of events, and we're going to hash it. And if the hash doesn't begin with a 1, we're going to change the data, hash it, change the data, hash it, until the hash begins with the number 1. So there you go. It took 55 goes. So it basically, what that did is it stuck a 1 as the data, hashed it, then a 2, then a 3, then a 4, then a 5. Eventually, 55, as you can see, the hash begins with a 1. Actually, in blockchain, the specification has to begin with a 0. That took 10 goes. The reason the little Bitcoin icon comes up is because in the actual Bitcoin blockchain, when you do this, what that transaction is at the end is you get a Bitcoin. That's where Bitcoin comes from. That's how you mine a Bitcoin. And in order to stop you spending that Bitcoin, you have to wait till another 100 blocks are mined before that actually becomes real currency. So it took 10 goes to get a 0. How many goes would it take to get 2 zeros? 631. So now I can add a third, 1,182. 4 is about as many as you can do in a presentation before the audience wants to kill you. From memory, 93,000 goes. If I start adding more zeros, the machine will start catching fire. In the actual blockchain specification, it tends to vary. The objective is it's the number of zeros that takes around about 10 minutes to find it. And it's, I think at the moment, last time I looked, it was about 12, I think it was 12 zeros. I could have got that wrong, 10 or 12 zeros. So basically what happens is, in order to protect that block, you specify a target. The target is many, many, many zeros, and then off goes the miner. And it sort of makes sense, because you're going through a list of hashes in order to find one that fits a certain criteria. And as you can see there, that's got 4 zeros at the beginning. So it is a stroke of genius, because what it does is it means anybody else that tries to break into this system has to change all of that data and go and find the hash for their fake data that matches the target. And what it's done is, and back to that picture of the pound coin, is that exchange of value. I'm actually exchanging value of CPU power and electricity for a Bitcoin that I will get from the system. So there is a definite value exchange happening. If we didn't have it, there would be no value exchange. And solving that puzzle is called proof of work. So that was the original Bitcoin, in the Bitcoin specifications, called proof of work. Some people have come up with other alternatives because proof of work is a pretty mucky way of saving your hashes. So proof of stake means I own some Bitcoin, or I own some kind of valuable currency in the system. Proof of burn, I've actually spent some currency. Authority, somebody's told me I'm allowed to do this. I've got space capacity, a massive machine, or whatever. But in many ways, these are all just value exchanges. I'm doing something to indicate that I'm a serious player in the system. And imagine there are 3 separate servers in the real Bitcoin network. There's obviously a lot more. Each one independently is going along, collecting transactions from Bob and Alice and solicitors and Brexit subverters, and sticking them all into the chain, calculating the hash, saving the block, taking the hash, starting on the next block. And in this particular picture, 1 has managed to create 3 blocks, 2 has created 2 blocks, 3 is streets ahead, has got 4 blocks. The longest chain in the entire Bitcoin network is the one that always wins. So the problem is, how does each server know what the others are up to? And that's the last bit of this presentation, which is what I think of as Facebook for machines. So that was 3 servers on the previous page. This is 5 servers. They don't all need to know about each other. They only need to know about a couple of other servers in the network. So in this example, something new happens, and let's say it happens on server 1, so it picks up a transaction from Bob, or maybe server 1 has just solved the puzzle and saved the block. It now needs to tell the rest of the network that it's got some new news. So it uses a protocol called gossip, where it doesn't tell everybody and it doesn't stick it in a central database. It simply tells the servers that it knows. So 1 tells 2 and 3 and says, I found a new block. And eventually 3, I think that was, tells 4, and then 4 tells 5. So 1 doesn't need to know about 5. They just constantly keep each other up to date with... It's a well-named protocol because gossip is literally how gossip spreads. You only tell your mates, then their mates tell their mates, etc., etc. And then everybody's happy because everybody now there are no secrets. I've got a little open source project where I play around with gossip protocols, and you can have thousands of individual kind of, in my thing, fake servers, and they all synchronize in milliseconds simply by hopping data from one to the other. And that was a particularly good use of the gossip protocol. So in summary, blockchain, what is it good for? Is it absolutely nothing? So as you can see from solving the puzzle thing, it is extraordinarily slow. It's deliberately designed to be such because it's a barrier in the way of the nasty hacker that wants to steal your money. On average, depending on the country that blockchain runs in, it costs about 5,000 quid of electricity for every single block, so it's not cheap. Because of the 10 minutes and all the transactions that are coming in, it can only actually save, in practice, about 3 to 7 transactions a second, because the block size in the specification is being limited. And as I found, I bought a load of Bitcoin ages ago just for fun, mostly because I just wanted to see what the experience was like. And I tried to sell it when it reached $17,000 just before Christmas, and I didn't make all the money I expected because while each server is mining all the transactions to create the next block, obviously some transactions have gone to other miners, and as the one that wins, you might be the unlucky one, and I was, to have your transaction on a server that just kicks it out. Then what happens is it has to try again. But after 6 hours, if you haven't been mined as such, then you're basically back to square one. But I don't think slow is necessarily bad. So, like my example with the solicitors and the wills, it was deliberate because wills are not high transaction. They do need to be stored in order, and they do need to be validated as being untampered. And if you have lots of machines that store the wills, then it becomes really hard to fiddle with them. It's really good for a digital currency because what do you want to create a currency, which is value? You want to have to put value in. I mean, we used to use gold and silver. Why? Because they're valuable. That's the whole point. You put value in and then value comes out. It's also good to get more funding for your startup because you could just use a database, but why not? You could use Bitcoin. On the negative side, and I found this out in the work that I did. Turns out that blockchain wasn't a great solution for what we were doing. We could have just used a database with some hashes cleverly distributed in them. Blockchain was originally designed as a public concept, so everybody could see what happens. Most companies don't want that. There are private alternatives, but I would argue they cease to become blockchain as we know it. And it's not teleportation. And more, and I was thinking as I was walking up today, this is a presentation I kind of wish I had done 6 to 9 months ago, because I'm now detecting a real strong swing now on Twitter of get very anti-blockchain. A friend of mine tweeted, blockchain sounds way cooler than the slowest database known to man. Got taken apart on Twitter for that. But there's definitely a big move now to be negative. So this, the guy in Hacker Noon said, so remember the blockchain spec came out 10 years ago. Nobody's really done anything to revolutionize the world yet. My final takeaway, remember Doctor Who put on a bow tie and said bow ties are cool, and it was kind of cool but not cool at the same time. Hashes are really cool, but only if you're someone like me. And you can use them in all sorts of different places. I designed a system based on hashes for British Gas to basically distribute traffic across multiple servers. Brilliant use of hashing. They're not complicated, so the code is always complicated, but I always just fall back to the whole corned beef thing. It's just taking data, chopping it up in a way that you can't go backwards. Connecting hashes together. A guy called Ralph Merkle came up with that in the 70s, I think. So none of this stuff is new. The gossip protocol, awesome. You can use it in loads of different places. Really simple to implement. Really simple to understand. And that's the hash of the word thank you.